Good evening again. The ABC of galaxy evolution. When we look out into the universe, we see lots of galaxies, many hundreds of billions, if not a few trillion galaxies. Some like this, beautiful face on, some we see apparently interacting with each other, like this pair that seem to be gravitationally bound to each other. Some have a lot of spiral arms, some have a couple of spiral arms. There is a lot of diversity of galaxies, and there's an awful lot of them. And the question we're addressing this evening is, how did we end up in a universe full of galaxies like this? And I would argue that the answer is the ABC, the three prime factors that determine how galaxies evolve. A is for accretion, because the galaxies formed in the first place by matter accreting under the influence of gravity from all of the matter made in the original Big Bang, 13.8 or so billion years ago. The B stands for black holes, because at the centre of most, if not every, galaxy in the universe appears to be a supermassive black hole. Some are very active, meaning that matter is falling in and perhaps a huge amount of energy is coming out of the region around the black hole. Some black holes are very quiet. They're quiescent. They're not actually feeding on any matter falling into them. And the C of the ABC is collisions, because galaxies grow by colliding and merging with other galaxies. In other words, galaxies are cannibals. They eat their neighbours and hence grow, and this occurs over many billions of years. So where does the story start? Well, it starts at the beginning, and I would argue it starts at the beginning of everything, which is an altogether different talk, about how the universe came to be, how it started as a tiny object about the size of a golf ball. In other words, everything that we can currently see in the observable universe being a sphere approximately 100 billion light years across, because we know the universe is expanding, we can deduce that everything that we currently see in the observable universe used to be a lot closer together. And if we go back far enough, if we wind the clock back far enough, we find that everything in the observable universe, currently 100 billion light years across, all of those objects used to be separated by just centimetres. I like to think of that as the cosmic golf ball. That expanded, and ultimately, when the universe turned transparent, resulted in the cosmic microwave background. That was when the light was first released in the universe. Up to that point, the universe was opaque. From this point onwards, the light was released, and that visible light that was released back 380,000 years after the Big Bang has now been stretched out by the expansion of the universe, and we see that as microwaves. So when we look all around us, we see the entire sky here unwrapped into this ellipse. We see the microwave background with some variations in intensity which correspond to the fact that the original golf ball, the cosmic golf ball, when the universe was a lot smaller, was not perfectly uniform but had small dimples in it. Dimples in the sense of small variations in density and temperature. But how did the universe evolve from something that was absolutely tiny to something that was rather larger when the cosmic microwave background was released? How did we end up getting from that universe to the universe that we see today, a universe being full of structures including huge numbers of galaxies? Well, we could argue that everything we understand about the evolution of the cosmic scale structures in the universe, or at least most of what we understand about cosmic scale structures, come from simulations. Yes, we have observations about what the universe looks like now, but in terms of understanding evolution, we rely on simulations to take us from the Big Bang through evolution according to the laws of physics as we understand them, and hopefully those simulations then present to us a universe which we recognise, a universe that we see when we make observations of what's out there. This particular talk, although there are lots of simulations, you can see a smattering of them on the left-hand side there, there's lots of different suites of simulations. And I've chosen to use one particular suite rather than jump around between different simulations. I've chosen the illustrious simulations as they are a suite that gives us the information and ideally the images and the movies that I'm going to use in this particular talk. So, as I say, the universe used to be a lot smaller. Basically, everything in the observable universe used to be just centimetres apart. And when the universe was this sort of size, the cosmic golf ball had small dimples in it, small variations in density and temperature, not simply on the surface, but throughout the volume that we currently call the observable universe. That gave rise to the variations we see in the cosmic microwave background. And it's those small variations in density that ultimately gravity grabbed a hold of, and over the course of billions of years, gravity caused those density variations to increase and decrease. In other words, the dense regions became even denser, the less dense regions became even less dense. And we ultimately ended up with the cosmic structure that we see today, which is a universe full of galaxies, not randomly or uniformly distributed, but distributed in a web-like structure. And we can see that if we run some of these simulations. So let me run one of these simulations, an animation, not of the entire universe, but of a small chunk of the universe, in which it's been filled with matter, and the matter isn't perfectly uniform, and the shade of blue here indicates the density. So it's not perfectly uniform. Perhaps you can see on the screen that you're looking at, there's a small mottling in the shade of blue representing slightly more dense, slightly less dense regions. And we're going to run the simulation and let gravity take a hold of these regions and see what happens. As regions get denser in this simulation, the colour gets brighter. So the white spots are the densest regions in which gravity is pulling matter together. And you can see that we're starting to form this filamentary structure, this web-like structure. The densest regions correspond to the regions where you can see these filaments, these lines of structures. Where they meet, we get very dense regions. That's where the galaxies are going to be most numerous. That's where we're going to see clusters and superclusters of galaxies. And we also notice that there are some regions of space in which the density has got further decreased by the effect of gravity. These so-called voids that we see when we look out into the universe and see where the galaxies are located, we find this sort of structure. Lots of galaxies that exist along filaments, and some regions of space that appear to be relatively devoid of galaxies. So it is thought through these simulations that we have some understanding of how this happens. It looks like matter flows through these filaments to the regions where filaments meet, and that's where you get the highest density and hence the nucleation sites for galaxies and clusters of galaxies. Matter effectively flows through the filaments and accumulates in these regions to make the early proto-galaxies, which ultimately give us the structures that we see today. But if a simulation is going to be realistic, then it's not simply a question of fill a computer simulation with matter and then let gravity do its stuff. We have to take into account the fact that when we're making galaxies, we're also making stars. And we have to take into account star formation and star evolution. Because although gravity is tending to pull matter down these filaments, when it makes stars, stars end their lives and you get supernova explosions which produce outgoing radiation, and also black holes which can produce jets and again outflowing radiation, which tends to impede the matter that gravity is trying to pull together. So there's actually a whole series of competing forces. Gravity is trying to pull everything together, but the shock waves and the blast of gas produced by supernova and black holes tend to push outwards. And so we can only get that balance right, we can only model it correctly if we take into account not only gravity, but also stellar evolution. We hope to be able to, through these simulations, explain the diversity of galaxies that we see. Here's just a smattering of some of the galaxies that we've picked out of the universe. And they've been sorted such that the spiral galaxies, which tend to be a little bluer in colour and rather flat in the sense of disc shaped, as seen from the side, very thin, as seen from the top, like pancakes. They often have spiral structure. Whereas on the right hand side, there's many galaxies that are somewhat redder or orangey in colour. They appear to be less well defined, more elliptical in shape, and have no apparent internal structure. And hopefully these simulations will not only tell us how matter is distributed throughout the universe, they'll also explain why we get a diversity of galaxy structures. So let's have a look at the accretion process, the A of the ABC. And let's have a think about how these simulations actually work. The Illustris project is a set of simulations that run essentially from zero, the Big Bang, or at least just after the Big Bang, to the present day. And then when we've got to the present day, we can compare the universe in the simulation with what we see and see if it makes sense. Does it actually give us a universe which is close to what we actually see? In principle, the simulation could run for much longer, but given that we don't know what the universe is actually going to look like in the future, there's limited use of using computer time to run the simulation beyond the present day. As I've just said, it's not just a question of throwing gravity in there and seeing how matter accretes, as in the right-hand picture. We have to take into account stellar processes such as black holes and supernova, the middle panel. And the elephant in the room is the left-hand panel. The universe is full of dark matter. So not only do the simulations have to take into account all the hydrogen and helium that's in the universe, we have to take into account the dark matter because that produces a significant amount of gravity, and that is going to influence the way the universe evolves. So we have to take into account lots of physics, of lots of processes, if we hope to get the simulations accurate, or at least realistic. The Illustris simulations, the first version of Illustris, ran for approximately 20 million CPU hours, CPU being a central processing unit. So between 2013 and 2015, the simulation ran and produced some interesting looking results, and the people that were running those simulations realized, well, this is interesting, but I think we can do better. In other words, we're not taking into account all the physics that we could take into account, so they refined and improved the simulation. So what did they call the next version of the Illustris simulation? Did they call it Illustris version 2? No, you can tell that they're sci-fi fans because they decided to call it Illustris, the next generation. And that's often been abbreviated simply to TNG. So when I refer to TNG, I'm just referring to the second incarnation of the Illustris simulations. Illustris TNG ran for 200 million CPU hours between the years of 2017 and 2019. And these simulations run on supercomputers such as the Cray here shown in the image. And if you want to put it in perspective, if you get a very fast desktop PC and run these simulations, it would take something like 20,000 years for the simulation to run to give you the same sort of results that you can get on a supercomputer over a period of a few weeks or a few months. The TNG simulations were carried out on 3 spatial scales, 50, 100 and 300 million parsecs, or if you prefer 150, 300 and 1000 million light years. This was done simply because if you want to get the large-scale structures of the universe, you have to deal with a simulation that deals with a large chunk of space, some 300 or more megaparsecs. But you can't do that at very high resolution because you simply don't have the computing power. So to get the highest resolution, you do it over a smaller scale, 50 megaparsecs, as indicated on the left-hand side there. And to make sure everything ties together, the high resolution in small scale and the modest resolution over much larger volumes, to make sure there's a continuous understanding of how structures develop, they also did an intermediate scale at 100 megaparsecs. And a reminder of light years to parsecs. 1 parsec is about 3 light years. Amateur astronomers tend to prefer to use light years because there's a certain understanding of how far light can travel in a year. But astrophysicists tend to prefer parsecs. And if we think of the Milky Way as being a fairly typical sort of galaxy, its diameter is about 150,000 light years, so that's about 50,000 parsecs, 50 kiloparsecs. And if we think of the distances between galaxies, let's take our local neighbourhood as an example. The distance from the Milky Way to the Andromeda galaxy is about 2.5 million light years, so that's about a megaparsec. So you can see a parsec is actually quite a useful yardstick, if you like. The distances between stars are typically parsecs. The distances between galaxies are typically megaparsecs. So it's a useful yardstick to remind yourself about spatial scales. So let's have a look at the TNG simulation, and let's zoom in to a particular area where we're actually looking at a region where filaments are meeting. The filaments of the web-like structure that I showed earlier. You can imagine a filament coming in from the top and a filament coming in from the left and a filament coming in from below. So matter is streaming down these filaments and collecting in this region central to this part of the simulation. You can see the spatial scale on the left-hand side. We're looking at a region of space that's comparable to the size of a galaxy. So let's run the simulation and see how matter behaves. It's fairly chaotic. Matter is coming in. Sometimes it gets caught by the gravitational concentration of matter that we can see in the middle here. Sometimes matter is escaping from this region because it's simply moving too fast. The lighter colours indicate the denser regions, and the darker colours indicate that matter is slowly decreasing in density. And after a little while, after 1 billion years or so, you can start to see the structure. In this case, the spiral structure of this galaxy is starting to show as matter is swirling around. There's always bound to be some rotation because it's almost impossible for matter to simply fall to a point. There's bound to be a small amount of rotation if you start with a collection of matter that has random motion in it. So we can see the development of spiral structures simply from the way matter gets funneled through filaments to the places where filaments meet. If we look at a particular chunk of TNG 300, the largest scale structure shown inverted in the background here, darker colours indicating where the galaxies are, just to make them a little easier to see. If we were to zoom in into parts of this simulation, we see individual galaxies. But the question is always, when you run a simulation, can we believe the results? Do the simulated galaxies look anything like the real galaxies that we actually see in the universe? And in this particular pane, we've highlighted 4 different types of galaxies. And we can ask ourselves, do we ever see pairs of galaxies that are very close, or pairs of galaxies that are interacting like this? Do we ever see galaxies that seem to have more like a shell structure? And the answer is, well, generally, yes, we do. On the left-hand side, we're showing actual galaxies, the antenna galaxy in this case, which bears a resemblance to the pair of galaxies in the top pane of the simulation. And similarly, the second pane showing galaxies that are interacting and tidal effects disrupting each other. Yes, we see that sort of thing in real life when we look out into the cosmos. And occasionally we see galaxies that have a sort of a shell-like structure, not necessarily spiral arms, not necessarily elliptical, but sometimes it looks like shells of stars around the central galaxy. And again, yes, we occasionally see those as well. But to be really sure that we are generating galaxies in the simulation that do bear a passing resemblance to galaxies that we see in the universe, we really need to drill down and look at the simulations on the 50 megaparsec scale rather than the 300. So if we look at the galaxies that have been seen in TNG 50, then we can get an idea of what they genuinely look like. And here we've got a selection of disk-type galaxies. On the left-hand side, the coloured maps here are showing us where the hydrogen is for various galaxies that have been found in TNG 50. In each of these panes, there's a galaxy seen face on, and just below it, what that galaxy looks like from the side. So these are all disk galaxies that look relatively thin when seen from the side and look pretty much like pancakes when seen from above or below. So the colour on the left basically is saying, where does the hydrogen end up? If we throw hydrogen and dark matter into the mix, we can ask ourselves, where is the hydrogen? And if we know where the hydrogen is, then we can take a guess as to where the stars are going to form, because we know the stars will be made of hydrogen and the hydrogen will be slowly fusing into helium. So if we know where the hydrogen ends up, where's the highest density of hydrogen, we can take a guess at where the likely star formation is going to be. And the right-hand side of these panes here shows, for the same set of galaxies, if that's where the hydrogen is, what would we think that galaxy is going to look like based on the stars that are going to be generated from those star-forming regions indicated by the hydrogen concentration. And there on the right-hand side we have a selection of various galaxies, and I think you'd agree that they look reasonably realistic. For each of these galaxies on the right-hand side, we could probably pick out a galaxy from a catalogue and say, yes, we do see galaxies that look like that. So we have some confidence that the simulations are producing what we might describe as realistic galaxies. And in particular, one thing that TNG 50 does produce is a whole load of galaxies with masses of order 200 billion solar masses, in other words, a mass of something like 200 billion stars. And as seen from the face-on view and indeed the edge-on view below it, these galaxies look a lot like the Milky Way. So they are, roughly speaking, the same mass as the Milky Way, and they seem to have the same structure. That picture in the top right could almost be a map of our own Milky Way. So TNG 50 generates lots of galaxies, many of which we recognize, and, somewhat importantly, it generates galaxies like our own. If a simulation generates lots of different galaxies, but it doesn't generate galaxies with 200 billion stars that look like our own, then the simulation is not doing a very good job. So this gives us confidence that the simulations are working well. Let's have a think about what's going on in the centers of galaxies, black holes. How do we know what's going on in the center of a galaxy? Well, we can look, for instance, in our own galaxy and we can map out, it's a rather tricky thing to do, but we can map out how stars are moving close to the black hole, close to the center of our galaxy. And we infer that there's lots of stars close to the center of our galaxy, all moving in orbits around something which must be massive to keep the stars in their orbits and orbiting in only a few years or a few tens of years. It must be a very massive object keeping them in orbit, and yet we can't see anything there. So the only thing that seems to fit the bill, something that's very massive, but it must be quite small because these stars are not crashing into it. So it's small enough to fit inside these various orbits of stars. Here we've mapped out a few of them that have been seen over a period of about 10 years or so. And the only object that could possibly keep all of those stars in orbit is something that's very massive and very small. And simply from Kepler's laws, knowing how the gravity of an object keeps another object in orbit by looking, for instance, at how planets go around the sun, we can deduce that the object that's keeping all of these stars in orbit has a mass of 4 million solar masses. In this talk, I'm using M circle dot as a symbol to mean the mass of our sun. There's nothing special about the mass of our sun, it's just a convenient unit, far better than kilograms or tons. The mass of our sun is used as a yardstick here for solar masses. So 4 million solar masses is the mass of the object at the center of our galaxy that's holding these stars in orbit. But given the geometry of these orbits, it must be very small, otherwise the stars would be colliding with it. It can't possibly be a collection of stars. It can't be, for instance, 4 million stars in a star cluster. That would agree with the mass, but 4 million stars in a star cluster would be far too big and these stars would be colliding with each other. So this object can only be a few light hours in size. In other words, rather smaller than our solar system. perhaps no bigger than the orbit of Pluto or something like that, and possibly a lot smaller. So the only thing that fits the bill is a supermassive black hole. It can't simply be a collection of stars. And we can do something similar either with stars or with the way gas is moving in other galaxies and figure out what the mass distribution in those galaxies are. And we find that there is, generally speaking, lots of evidence for massive objects at the centres of various galaxies. So in the centre of ours, supermassive black hole, hereafter just abbreviated to SMBH, we know that in our galaxy 4 million solar masses. But that's by no means a particularly large value. For instance, in the middle of Centaurus A, we can't see it in this particular image, but right at the middle we think there's a supermassive black hole of some 100 million solar masses. And again, that's by no means the maximum that we've seen in any galaxy. If a star gets too close to a black hole, it can be ripped apart. The tidal forces that exist around a black hole can tear a star apart. And notice in this little animation here, the material of the star doesn't simply fall into the black hole in much the same way that water can't simply go down the plug hole when you empty a bath. It tends to circulate. And in a so-called accretion disk, the matter is accreting before it goes and gets swallowed up by the black hole, and in the process of circulating, all of the matter here is interacting with all of the other matter, producing a lot of heat, a lot of radiation, and possibly jets, as indicated again in this animation. We don't really understand all of the details of how infalling matter can give rise to jets coming out in the polar regions of a black hole, but they seem to be a relatively common feature. Converting matter into radiation is actually very efficient for matter falling into a black hole. It's been calculated that if you were to tear apart a few stars or to have a lot of gas and let it fall into a black hole, it could be that some 10 or 20 or 30% of the matter might be converted into energy, ultimately into radiation or in the energy of the jets. That is a very efficient process. For instance, if you compare it to what's happening in our sun, converting hydrogen into helium, that is a fusion process in which perhaps less than 1% of the total mass is converted into energy. So stars, in a sense, are only 1% or actually less than 1% efficient. But if you drop matter into a black hole, you might get efficiencies of 10 or 20 or 30% in terms of how much of that matter is converted into energy. We can see some of these jets. Here's M87, an enormous galaxy that's not too far away. And here we can see the jet, but it's not very clear. So let's zoom in with a Hubble Space Telescope image. There's the center of the galaxy in the top left. And we think there's two jets coming out of this galaxy. One jet is coming towards us and appears quite bright. That's the one we can see coming out to the bottom right. We think there's also a jet going off in the opposite direction, away from us. And because of relativistic effects, any jet going in the opposite direction is going to be less bright. And although it's there, we can't really see it. So it looks like there's one jet, but there probably are two. If we want to see what's going on right in the centre there, well, the Hubble Space Telescope simply hasn't got enough resolution. But if we tie together radio telescopes across the world as a huge interferometer, then it's acting like a telescope roughly the size of the Earth. And then we can start to get the resolution we need to see not the jets themselves, but what's going on for the matter falling in towards the black hole. And here we see what's going on in the middle of the galaxy M87. We see the accretion disk, here shown as an orange donut, if you like. It's thought that this supermassive black hole has a mass of some 6.5 billion solar masses, considerably more, 1,000 times more than the mass of the black hole in the centre of our own galaxy. What's happening here is matter is falling into the supermassive black hole, forming this accretion disk. We're not really seeing what's going on in the middle because any light that's trying to get to us from the middle region of this image is being extremely distorted by the very high gravity of the black hole and is effectively finding it impossible to come towards us. It's being bent away from us. So we're seeing this sort of donut structure, and we're seeing some parts are a little brighter than others. And it's thought that what we're actually seeing here is the accretion disk. You might think that, well, are we seeing the accretion disk from, as it were, on top, because it looks like a complete donut? But actually, we would see something very similar regardless of the angle with which we're observing it. And this little animation shows why. The accretion disk might look like a donut as seen from above, but even seen from the side, it doesn't look like, for instance, Saturn's rings. It's not a question of the accretion disk disappearing when you look at it from the edge on. Because of the distorting effects of the black hole in the center, we're seeing light from the far reaches of the disk coming over the black hole, and we're seeing light from underneath the disk at the back coming below the black hole and being bent towards us. So we're seeing essentially all of the accretion disk all of the time because of the way light is being distorted by the black hole. And notice that because of rotation, in this particular animation, it's brighter on the left than it is on the right, because of the way it's rotating, and any matter coming towards us will tend to look brighter than matter moving away from us. So that's why we always tend to see a donut when we look at these images, regardless of whether we're looking at the accretion disk from above or from the side. So that's the 6.5 billion solar mass accretion disk seen around the black hole of M87. And that black hole is called M87 star. In much the same way, what's going on in the center of our own galaxy is called Sagittarius A star. Remember, this is a supermassive black hole which is substantially smaller by a factor of 1,000. It's only 4 million solar masses. But the center of our galaxy is a lot closer than the center of M87. As luck would have it, M87 is about 1,000 times further away than the center of our galaxy. And its black hole is about 1,000 times bigger. And so coincidentally, that means that in terms of how large would you expect this accretion disk to appear on the sky, it's very similar in terms of how many arc seconds. Well, actually it's measured in micro arc seconds because we're talking about a very small structure here. So the size on the sky of this feature in our galaxy is very similar to the feature we've just seen in M87. We appear to have a slightly different structure. There appear to be one bright area and a couple of other bright areas. One of the difficulties in taking this image in the Milky Way is it's much smaller, and we think that matter is rotating in this accretion disk much faster than it is in M87. And so it's not possible simply to take the equivalent of a long exposure to acquire the data to get these images, because if you take a long exposure of Sagittarius A star, because of the movement of the matter around the black hole, it would blur out the features that we're trying to see here. So it was a technically more challenging case to get this image than it was to get M87, which is why the M87 image was released first, and then it took a few more years of analysis to generate this image of Sagittarius A star. We should perhaps remind ourselves of what the true sizes are, even though they look similar in terms of the size on the sky. On the left-hand pane, there's the size of the M87 accretion disk, scaled to show you what it's like compared to the scale of our solar system. There's Pluto's orbit, and there's the size of the M87 accretion disk. And just to give us a sense of scale, if the Sun is at the centre, that's how far Voyager has reached so far after 50 years travelling away from the Sun. By comparison, Sagittarius A star, the accretion disk there, is larger than the size of the Sun, but actually smaller than the size of Mercury's orbit. So you can see if they were drawn to scale, then the accretion disk of Sagittarius A star in the Milky Way would be absolutely tiny compared to the accretion disk that we see around M87. a reminder of just how much energy is pouring out of some of these supermassive black holes. Here's an image of Hercules A. This is an image taken in visible light with the Hubble Space Telescope. There's the rather nondescript galaxy itself, Hercules A. It looks like just a fairly boring elliptical galaxy. And if we imagine just for the moment that this galaxy which appears to be next door, let's imagine that that galaxy is at a similar distance. I'm not sure it actually is, but let's just imagine that is. That galaxy is perhaps about the size of the Milky Way. So we can see that the Hercules A galaxy itself is massive compared to the size of the Milky Way, some 100 to 150,000 light years in diameter. But the supermassive black hole at the centre of Hercules A, although it would be far, far, far less than 1 pixel in this image, is producing so much energy and generating jets that are coming out not only of the black hole, not only of the stellar region around the black hole, not only coming out of the galaxy itself, but if we look not in visible light of Hercules A and ignore for the moment the size of the Milky Way, that's just there for scale. If we look in the radio, we see that the jets coming out of this galaxy are absolutely huge. Whatever is pouring out of the region around the black hole, it is producing jets not only that travel across the galaxy itself, but leave the galaxy and go slamming into the intergalactic medium where we see these shock waves in pink that show up in radio wavelengths taken here with the very large array. So we can get a feel for the fact that although the black hole is tiny on the galactic scale, its effects can be enormous. If a supermassive black hole is feeding voraciously on its surrounding material, in other words, if gas and stars are falling into the black hole, then the galaxy is referred to as an active galactic nucleus. The nucleus itself, the black hole at the core, is the engine that gives active galactic nuclei their label. The most energetic active galactic nuclei are called quasars. These were one of the earliest types to be seen because they can be seen over such vast distances. So we believe that supermassive black holes are basically the engines that allow quasars to emit so much radiation they can be observed from huge distances. And during COVID, I decided to set myself the challenge because I couldn't go out and socialise. I asked myself, what's the most distant object I can photograph, not using a telescope, but what's the most distant object I can photograph with my camera? And I found a quasar which was at a redshift of 4.3. That means that this quasar is at a distance of 25 billion light years. And even at that distance, it was possible to catch it with a camera, even without using a telescope. Yes, I admit it's not particularly spectacular. There it is between the two red lines. If we blow it up, there's not much to see. It's basically 1 pixel in this image is this quasar. But this quasar is at a distance of 25 billion light years. And if we work out from the expansion of the universe, how fast is this quasar receding from us? Well, it's at such a vast distance, this object is actually receding from us at twice the speed of light. It was receding at twice the speed of light when the light left it, and it's still receding from us at about that speed. So at this enormous distance, 25 billion light years, it is still possible to catch the light from one of these objects, and this is simply a reminder of just how much radiation is coming out of a quasar powered by the supermassive black hole at the heart of this galaxy. That's still a bit of a mystery exactly what the relationship is between the black hole at the centre of a galaxy and the galaxy itself. If we plot vertically on this axis the black hole mass of various galaxies that we've studied, and horizontally the galaxy mass, strictly speaking, not the full mass of the galaxy, but the mass of the bulge at the centre of the galaxy rather than the mass of the spiral arms itself, we see that the Milky Way is down here relatively close to the bottom. It has a rather modest sized black hole at its core, and the Milky Way is not a particularly large galaxy. Compare that with M87 at the other end of this plot, an absolutely monster-sized galaxy with an equivalent monster-sized black hole, as we've said, 1,000 times larger than our own supermassive black hole. So there appears to be a relationship between them. Yes, there's a lot of uncertainty in these measurements. Sometimes it's very difficult to pin down the mass of a black hole at the centre of a galaxy. But there does appear to be a relationship between them. Bigger galaxies have bigger black holes. So it leads to the intriguing question of chicken and egg. Did black holes form and then galaxies collapse around them? Or did stars form, which then some stars died, produced supernova, some of those stars died and became black holes, and the black holes merged? Did galaxies start to form and then black holes come later, or vice versa? It's difficult to tell from the simulations because we're not sure what the actual relationship between them is. The James Webb Space Telescope is trying to address this problem. The James Webb Space Telescope is looking back in time as far as it can. Looking at the most distant galaxies, the James Webb is able to see back to that first 1 billion years of the universe's history. And so far, it's found galaxies that are rather brighter than we would expect. Not necessarily any bigger, but certainly brighter. And it's thought that these early galaxies are bright because of the light that's coming from the supermassive black holes at their centres. And this would imply, if this turns out to be correct, that supermassive black holes appear to have existed in the very early universe, whilst galaxies were still developing. So maybe supermassive black holes came first and then galaxies form around them. But I think the James Webb needs to do far more and get much more data before we can definitively say that is the relationship. It's probably a more symbiotic relationship in that they tend to evolve together, but we need more data before we can really tell. Let's have a think about the C of the ABC. We've thought about accretion, we've thought about black holes. Let's think about collisions, because galaxies evolve over billions of years by colliding and merging. When we look at a single static image of a galaxy, we can be tempted to think, well, that's very nice, but it's effectively static. Yes, we know they're rotating, and after 100 million years or two, we might see the galaxy rotate slightly, but perhaps it would look pretty much the same. However, over its lifetime, it can evolve due to interacting with other galaxies. So some images show us galaxies in isolation. But we now have lots of images from the Hubble Space Telescope and from James Webb that show us that galaxies interact with each other. And this turns out to be much more common than we appreciated some decades ago. So we now have plenty of examples of snapshots in which we can see galaxies that are tidally disrupting each other. In some cases producing some rather beautiful structures. But in virtually all of these cases, because they're only snapshots, we can't really gain the full understanding. We can't appreciate the influence of collisions and mergers simply from a lot of snapshots like that. We can only really appreciate how mergers work through simulations. And again, we can use TNG simulations, not looking at one galaxy, but by looking at a rather larger chunk of space and asking ourselves, how does this behave? So here you can see an absolute galaxy soup, and you can appreciate that simply by following one or two galaxies, you can see that they are continually interacting with each other. There's one there that's been tidally disrupted. We've got a galaxy coming in from above and below. They are going to pass each other, and then they are going to merge together. and then they are going to settle down as one even bigger galaxy. And along the way, they're going to start hoovering up some of the smaller galaxies as well. If I just run that simulation one more time, you can see all sorts of tidal disruptions as galaxies sometimes get close to each other. Sometimes a small galaxy can pass a larger galaxy. And as this galaxy comes in from above and comes in from below, we can see other galaxies that are getting severely disrupted by their proximity. This one, for instance, coming off at the top, used to have spiral arms, but now it's been completely disrupted by its passage past another galaxy. And it's only when we simulate thousands of galaxies at a time that we can start to appreciate just how many interactions there are over billions of years, over this relatively large chunk of space. When we look at galaxy clusters, again, if we simply take a snapshot, we don't necessarily fully appreciate what it is we're looking at. When we look at galaxy clusters, we tend to get a lot of the more redder elliptical structures, as you can see here, compared to the rather bluer spiral structures that we're familiar with when we look at individual galaxies. And that's because when we're looking at the crowded interior of a cluster, the galaxies are much more likely to collide with each other than when we're looking at individual galaxies that aren't part of a large cluster. So if crowding means more collisions, and when galaxies collide, for instance, when spiral galaxies collide, they can often disrupt each other's spiral arms, and the resulting galaxy can look more elliptical than spiral. And that's why we tend to find that when we look in galaxy clusters, we find a lot of elliptical galaxies. That's where they are most crowded and most likely to collide. We can simulate what's likely to happen in our immediate vicinity by thinking of what's going to happen to the Andromeda galaxy in the bottom left and the Milky Way in the top right. Here, M33, the Triangulum galaxy, is just a spectator. We think in a few billion years, Andromeda and the Milky Way are going to collide with each other. It's unlikely that any stars hit each other, simply because stars are so far apart. But the galaxies will pass through each other, and they will tidally disrupt each other, and there'll be a lot of interaction of all the gas and the dust in the two galaxies, even if the stars themselves don't collide. And after a few billion years, they will eventually settle down into one larger galaxy. If we think what that might look like as perceived from the Earth, if we assume the Earth survives, it might be that the Sun gets torn out of the Milky Way. Well, if it does, the Earth will go with it. It's not a cataclysmic event as far as that's concerned. There's the Andromeda galaxy in our sky as we see it today, and of course the familiar band of the Milky Way crossing the sky. If we think what's going to happen in a billion years, Andromeda is going to be coming towards us. So for those of you who like astrophotography, if you want a picture of the Andromeda galaxy, you're not going to need a telephoto lens in the future. You can just sit there with a wide-angle lens and Andromeda will fill our skies. And then as the two galaxies pass through each other, remember, stars don't collide, but the gas and the dust will. And so there'll be disruptions to all of the hydrogen clouds in both galaxies, and that will trigger these clouds to collapse, and there will be a riot of new star formation. So far from galaxy collisions being apocalyptic and the end of a galaxy's life, far from it. You could argue it's a sort of rebirth, because there will be a vast number of new stars being formed for at least a while before the two galaxies settle down. They will pass through each other, and Andromeda will come out the other side of the Milky Way, and of course the spiral structures of both galaxies will be disrupted, and eventually they will settle down. And perhaps for a while we'll see a relatively elliptical galaxy with a nucleus that was the nucleus of Andromeda, and perhaps a second nucleus which was the nucleus of the Milky Way. Two supermassive black holes which will orbit around each other for quite a while, until eventually those two supermassive black holes will coalesce into one even larger supermassive black hole. What are we going to call this galaxy when the Milky Way and the Andromeda galaxy merge together? Well, we can't call it the Milky Way anymore. We can't call it Andromeda anymore. We'd have to call it Milky Andromeda or Andrilke or it doesn't matter. We've got 5 billion years to figure out what the name is going to be, so we don't have to worry about that too much. But it's interesting to note that there's every possibility that when our two galaxies collide, enormous amounts of matter are going to be gobbled up by our supermassive black hole and the one in the centre of Andromeda. At the moment, both of those supermassive black holes are relatively quiescent. Very little matter is falling into them. But when we have a galaxy collision, it's quite possible that enormous amounts of matter are going to be flowing into those black holes, and as a result, huge amounts of radiation coming out. So perhaps in a few billion years, the Milky Way and Andromeda galaxy complex perhaps could turn into a quasar and might even be visible from the other side of the observable universe, much like quasars that are very distant from us are visible to us now. So I've been telling you about the ABC. Accretion under gravity pulls stuff together. Bearing in mind we also have to take into account stellar processes which tend to push back and stop everything simply collapsing to nothing. Black holes are important, but we don't understand fully the symbiotic relationship between black holes at the centres of galaxies and the evolution of galaxies themselves. Perhaps the James Webb in the next few years will give us more information about very early galaxy formation in the first few 100 million years that will answer the question of chicken and egg, which came first. But we do know that over the lifetime of a galaxy, collisions and mergers dictate the way galaxies behave. The fact that large galaxies tend to cannibalize smaller galaxies, and ultimately lots of galaxies within a galaxy cluster will end up merging together in the very long scale time scales of the universe. So next time you see a galaxy, whether it be on a web page or in a magazine or even a small fuzzy blob through a telescope, next time you're admiring a galaxy, remember how they came to be. The ABC of galaxy evolution. Thank you all for listening.